Assalamu alaikum. So today we are starting the final topic, matter and radiation. Matter and radiation. So don't write what I'm writing now. We know that heat can be transferred in three methods. One of the method is transmission. Then we had conduction. Sorry, conduction, convection, and the third method, it's radiation. So in case of conduction and convection, we need a medium. A medium is necessary. But in case of radiation, a medium is not necessary. Okay, we don't need a medium to transfer heat. Then how is heat transferred? Here, heat is transferred as electromagnetic wave. So it will show all the characteristic of electromagnetic wave, its speed, its characteristic, refraction, reflection, all of those characteristics is shown by radiation. And this is the method that the heat from the sun reaches the earth. Okay, so let's write down. The process of transmission of heat, the process of transmission of heat from one place to another, from one place to another, without requiring a medium. Without requiring a medium, is radiation. Is radiation. So the best example, feeling the warmth, feeling the warmth of fire, of a fire, standing close to it. So when you're close to a fire, you don't need to actually get very close, or you don't need to touch it, but still you can feel its warmth even when you're standing at a certain distance. So that is due to radiation. And then heat from the sun, heat from the sun reaching the earth. So as I said, radiation is electromagnetic wave. Okay, so it's going to have certain properties. So let's look at those properties. Properties of thermal radiation. Energy is transmitted in the form of electromagnetic wave. We discussed. So we know the speed of electromagnetic wave is 3 into 10 to the power 8. Medium is not required for propagation. And especially, it does not heat the intervening medium. Now, let's say when radiation is going through a certain medium, it does not heat up. It won't heat this medium. There is no heat due to this wave going through this. Okay? It obeys the laws of reflection and refraction. It is not affected by electric and magnetic field. Uh, we already know that electromagnetic waves are not affected by electric and magnetic field. Next, intensity of radiation is inversely proportional to the square of the distance from source. So that means I, the intensity, it is inversely proportional to the separation. When you're too far away, when you're at a distance r, if the intensity you felt is I, when you go to a distance of 2r, the intensity will decrease by 4. So it is proportional to the square of the distance from the source. Okay, inversely proportional to the square of distance from the source. Once you have noted, let me know. And I hope these points are clear. I don't need to explain them one by one. Done. Sajan Shahama. Okay, next let us look at what are the factors that affect the rate of thermal radiation. So we know that when we have an object that is very hot, it is really hot, then the amount of radiation it is going to emit if the object is really hot, the amount of radiation it is going to emit is high. The rate of emission is high. And do you all know that black color body, a black color body, it absorbs a lot of energy. It will absorb a lot of energy as well as it will emit a lot of energy. I mean, it will radiate a lot of emission. That means this nature of surface, the color or the material, all of them uh, affects the rate of radiation. When you have a black color body, it radiates more than a white color body. So the nature of surface also affects the rate of radiation. And then also the size. When we have a smaller size but same temperature, the radiation here is going to be less than this. Okay, so these are the factors that affect the thermal radiation. The rate of emission of heat from a body depends on the following factors: temperature of the body, nature of surface, surface area of the body. Copy it down. I hope it's clear and there's nothing to explain in much, right? If you need any further explanation, make sure you ask them. Then, so we can show that the rate of emission of heat depends on the following factors by a very simple experiment. The above, the above could be the above could be demonstrated using a Leslie's cube and a thermopile and a thermopile. Leslie's cube, it is nothing but a cubical shaped container. A cubical shaped container it's a cubical shaped container. Its surfaces are different from one another. On one side, we will have a rough surface. On another side, we have a smooth surface. On another side, we have a white color painted surface. So the surface differs. Okay, so this is a Leslie's cube. Leslie's cube. And from this Leslie's cube, at a certain distance, let's have a thermopile. I will let you know what's a thermopile. So this is a thermopile. Thermopiles, they are made up of we call them as thermocouple. So what's a thermocouple? Thermocouple is a measuring device. We can measure temperature. We can measure temperature difference by measuring the current. So this is a millimeter. So we have two different wires. This is a millimeter. First one is, let's take it as wire A. This is wire A. And this is wire B. They are made up of two different wires, wire A and wire B. And we have two junctions. This is a junction and this is another junction. So what we do is we place them at different temperatures. This one at theta degree Celsius, this one at 0 degree Celsius. So we call one junction as cold junction. So here this is the cold junction and this is the hot junction. Now we have two different wires. In two different wires, we know that their resistance will differ. So depending on the resistance on these two wires, it will be convenient for the charges to pass through one of the wire, maybe through wire A or through wire B. So here, because of that, a EMF is induced. Okay, so we can tell due to temperature difference, EMF is induced. EMF is induced. Measuring the EMF, temperature is determined. Temperature is determined. Now, this is a single thermocouple. So this is a thermocouple. Then what is a thermopile? Thermopile is combination of thermocouples. So this is the cone shape. So it will direct the radiation into this thermopile. So we can show the thermopile connected end to end. Thermocouples connected end to end to construct a thermopile. several thermocouple are connected in series to construct a thermopile. So now we are not going to measure the temperature, but now you must get the idea. If radiation falls on this will show a reading. If the radiation is high, the reading will be high. If the radiation is low, then the reading will be low. Okay. So now we are not going to measure the temperature, but to get an idea about the energy or the radiation. Is it clear? Have you all drawn the diagram? Should I scroll up? Has everyone drawn this diagram? Draw. Once you complete this, let me know. When you're done, let me know. The job done. Okay, Leslie's cube. Leslie's cube is a hollow cube made up of metal to compare the emissivity of different surface. That means how much it is going to emit or it is going to radiate, as we discussed previously. Okay, so using Leslie's cube, we can compare. So, as I mentioned, this Leslie's cube has different surfaces. Now, it doesn't mean it necessarily should have these types of surfaces. This is just an example. Okay, so in this example, let's take that one surface is a lamp black surface. So it is a black surface, and another surface, it is covered with paper. So it's slightly different than the previous surface. And then we have a very polished surface, a very well polished surface. So here, the radiation is going to be very less. And then we have a surface which is covered with white paint. So this is an example. That means in a Leslie's cube, we are going to have 4 different surfaces. Okay. So just note it down quickly. So let's see how we can use this Leslie's cube to compare the emissivity of different surfaces. Okay. So we have to prove that it depends on temperature. It depends on temperature. It depends on the nature of surface and the surface area. For that, first, let's prove that the radiation depends on the nature of surface. So it's easy. That experiment is easy. Number one, nature of surface. Now we are going to prove that radiation depends on the nature of surface. So I will explain. After that, I will put the note. You can copy. Now let's say this is our Leslie's cube. You don't need to draw this. So in this Leslie's cube, as we discussed previously, we have different surfaces. This surface is different from the surface on this side. But we know that this radiation, the rate of radiation also depends on the distance. It will also depend on the distance. Therefore, we place the thermopile at the same distance. Okay, we place the thermopile at the same distance and pour hot water into this, pour boiling water. So when we pour boiling water, now the temperature is same, right? Temperature is same and the distance is same. What we are going to change is we are going to change the nature of surface. For that, we will simply rotate this Leslie's cube. Okay, when we have compared, when we have got the reading of the millimeter for the surface, let's record. So surface reading, let's take a record and now bring this surface and check the surface and the recording. So we will have 4 different readings. So using those readings, we can understand that which one will emit, which one will be a good emitter or good radiator, which surface. The black color surface will be the best radiator. And then we will have the paper, surface covered with the paper, and next we will have white paint. So the white surface, and finally we have the polished surface. Is this idea clear? The thermopile is placed at equal distance from each face of the Leslie's cube, which is filled with boiling water. Although all faces are same, so when we pour boiling water, the same temperature is same, right? But when we look at the reading, black color surface radiates the most and the polished surface radiates the least.